Warm welcome to this video introduction to heat transfer. As a part of FDP 201X IIT Mumbai workshop, we are introducing this video introduction to heat transfer. We are from RC1402 Vardhaman College of Engineering Hyderabad and we are from Mechanical Allied Groups, the batch number 006. So before going to introduction to heat transfer, let me ask one question. The focus question is, what is the difference between heat transfer and thermodynamics? You can pause the video for a minute while you think about this and then write it down in a notepad or document in your device. Once you complete writing, you can resume the video. I hope you have written the definition, the difference between heat transfer and thermodynamics. So let me tell you my answer that I have written. So the difference between heat transfer and thermodynamics is, thermodynamics deals with equilibrium state of matter and how much heat is transferred, how much work is done, and it is dealing with the final state of the system. Whereas heat transfer deals with non-equilibrium states and with what mode heat is transferred, at what rate heat is transferred, and temperature distribution within a body. This is the main difference between thermodynamics and heat transfer. So let us introduce the different modes of heat transfer. So what are the different modes of heat transfer? The first mode of heat transfer is conduction, the second one is convection, and third one is radiation. So what do you mean by conduction? Heat conduction is a mechanism of heat transfer from a region of high temperature to a region of low temperature within a medium or between different medium in direct physical contact. So it is a molecular phenomena. In conduction, energy exchange takes place by the kinematic motion or direct impact of molecules. Pure conduction is found only in solids, that is, it is more predominant in solids. So convection, what do you mean by convection? So when there is a fluid solid interaction, then there is a meaning for the term convection. Due to the bulk motion of the fluid over a solid body, the mode of heat transfer will be convection. So it needs a fluid interaction between a solid and fluid. So third mode is a radiation mode of heat transfer. So it does not need any matter. Transmission of energy is by electromagnetic mechanism. So what are the different applications of heat transfer with respect to the mechanical engineering? So different applications of heat transfer are cooling of turbine blades, regenerators, condensers, steam generators, cooling of IC engine components, cooling of circuit boards, design of chemical beds, curing of concrete beds, finding thermal expansion of the bridges, railway lines, suspension cables, etc. So what are the basic laws of heat transfer? The different basic laws of heat transfer are Fourier law of heat conduction, Newton law of cooling, Stefan-Boltzmann law. So coming to the first one, Fourier law of heat conduction, it tells about the rate of heat conduction Q is directly proportional to the area which is perpendicular to the direction of flow, that is normal to the direction of flow, and temperature gradient in that direction. So mathematically it is equal to Q is directly proportional to A dt by dx. A is the area which is perpendicular to the flow of heat, dt by dx is temperature gradient, Q is heat flow. So when you remove that proportional symbol, we will get one constant, that is K, that is called thermal conductivity. So the units for thermal conductivity is watt per meter Kelvin. So from the Fourier law of heat conduction, Q equal to minus Ka dt by dx. So what are the different assumptions of Fourier law of heat conduction? So the different assumptions of Fourier law of heat conduction are: conduction heat takes place under steady state conditions. Heat flows in unidirectional, temperature gradient is constant and temperature profile is linear. There is no internal heat generation. So bounding surfaces are isothermal in character. Material is homogeneous and isotropic. So coming to the thermal conductivity, it is the ability of material to conduct heat. So thermal conductivity of most of the metal decreases with increase in temperature. So aluminum and uranium are exceptional. In most of the liquids, thermal conductivity decreases with increase in temperature. So water being exception. In case of gases, the value of thermal conductivity increases with temperature. So the second law is Newton's law of cooling. According to Newton's law of cooling, the rate of heat transfer is directly proportional to the area exposed to the heat transfer and temperature difference between the fluid and the surface. So mathematically it is equal to Q is directly proportional to the area and difference between the surface and fluid temperatures. So when you remove that proportional symbol, we will get one constant called H, where H is heat transfer coefficient, which is the units is watt per meter square Kelvin. So according to Newton's law of cooling, Q equal to HA Ts minus Tf or Tf minus Ts, which greater minus lower value. So the third law is Stefan-Boltzmann law. So according to Stefan-Boltzmann law, heat transfer rate is directly proportional to the area and fourth power of absolute temperature. So mathematically it is equal to Q is directly proportional to A into T power 4. So when you remove that proportional symbol, you will get one constant called sigma, which is Stefan-Boltzmann constant, which is the units is watt per meter square Kelvin power 4. Thank you very much.